Hi guys, welcome to our third lesson in the renal section. Today we're going to talk about basic transport mechanisms across epithelia. Some of this will be some review for you. And in fact, there are sections of the notes that are marked review that you actually don't have to go over if you think you remember all the material. I won't test you directly over those sections, but I will assume that you know them. And then we'll talk about renal handling of organic solutes, okay? So our first figure is just here to more or less demonstrate that our nephron is entirely really made up of epithelial tissue. And you should recognize that, and you should recognize that the characteristics of this epithelial tissue vary all over the nephron. And the reason they vary is because each region of the nephron has a bit of a different function, which is, what we're gradually revealing here. And so the structure varies with the function, and you should recognize that. Do also recognize that I will not test you on the specific morphological features of all these epithelia. Somebody else might, I will not. That is not the purpose of this figure. You don't have to memorize the details. I just want you to recognize that it's epithelial tissue and it varies from section to section throughout the nephron and why that is. There are a couple of review sections in the notes that you are not directly responsible for, but I will assume that you know them. So if you feel like a good review is called for, you should go over those sections. They're not very long, and they just cover basic transport and basic epithelia, what the difference is between paracellular and transcellular transport, that sort of thing, okay? So having said that, let's go over the transport of sodium across the epithelium here. And I'm going over this because I consider it to be the prototypical sort of epithelial transport. So this is just here to demonstrate the 4 steps of the transport as they take place across renal epithelia pretty much everywhere throughout, okay? And in the vast majority of the transport mechanisms that we're going to talk about, you can find some variation of these 4 steps. So everything really starts and is driven by the sodium-potassium ATPase in the basolateral membrane. This is the basolateral membrane. Most of my transport figures look just like this. And this is the basolateral membrane, and then you'll know that because it faces the interstitium. Step 1 is the sodium-potassium ATPase transport in the basolateral membrane. And the vast majority of the time in epithelia, you will find this transporter there, and it is usually important for driving transport. And what it does is you transport sodium out of the cell, you transport potassium in, and that keeps the sodium concentration low inside this cell. And because the sodium concentration is low, you can use the sodium gradient across the apical membrane to drive transport. And that is usually step 2. Now in this case, because it's just sodium transport, sodium actually goes through a sodium channel from high concentration in the tubular lumen to now low concentration in the cell, and that low concentration is maintained by the sodium-potassium ATPase. So this is facilitated diffusion. It's the sodium just goes through the channel into the cell. And so you can see the sodium goes from the tubular lumen through the channel into the cell and then out of the cell through the sodium-potassium ATPase, and that is its pathway. Now you'll often find that step 2 will be sodium transport, but it will be coupled to transport of another substance, so that what you'll have is secondary active transport where the sodium goes down its gradient, and that's coupled through a transporter which will be transporting some substance either out of this cell or into this cell, which will be using the sodium gradient to transport that substance up its gradient. And a good example of that will be glucose, which we'll go over in a minute. Okay? So that is step 2, and also notice that anions follow the sodium. And that is because you have to maintain electron neutrality. So whenever you transport a cation, you have to transport an anion to go with it to maintain electron neutrality. That is very often chloride. And in this case, it is mostly chloride, as you will find out in a future lesson. And then that anion will also be transported across the basolateral membrane, okay? Step 3 is water movement. And water can either take place through aquaporins, transcellularly, across both membranes, or it can take place through the tight junctions if they're not so tight, and they'll allow water to go through. And water follows your solutes. So if I'm transporting sodium and chloride from the tubular lumen through the cell into the interstitium, then water, that will increase the osmolarity here and set up a gradient for water, where water will follow, and it will go down its concentration gradient from the tubular lumen to the interstitium. Do bear in mind that as the solutes go, so goes the water, and that is how water moves everywhere in the body. There are no active water transporters, okay? So water movement is step 3 most of the time. And then step 4 is equilibration of the interstitium with capillaries. Basically, all the stuff moves from interstitium into the capillaries and is carried away. Okay, so the vast majority of the time, epithelia are going to work to transport some substance through some variation of this 4-step transport process. And again, I just use sodium as sort of a typical example of that. Okay. So I'm going to stop there, and I'm going to start the next video where we will talk about transport of organic substances, primarily glucose, and then we'll finish up with urea after that.